So we'll start off with what concepts we're going to cover in this session. The main topic of interest will be generating Green's functions for 2D and 3D problems, and for the broad context of situations where we have lateral variations in the 3D structure so that we can't use simpler methods or semi-analytic methods to compute those Green's functions. In the process of computing Green's functions and going through the sort of overall workflow, many cases in computing Green's functions, you want to compute the solution not just at the ground surface, or even, you may not even want the solution of the entire ground surface. You want it at your observation sites, such as your GPS sites or seismometer locations. And so we'll make use of solution of the output at a specified set of points. The component for this is called output solution points, and we'll show you how to use that within the context of Green's functions. But the output can also be used whenever you run a forward type of simulation. In computing the Green's functions and performing an inversion, we'll use post-processing of the HDF5 output using a Python package called h5py. The way you access the HDF5 file using h5py is very similar to using MATLAB. Then you basically are able to go in and grab values for, say, the coordinates of the vertices or your displacements or your slip in about 1 or 2 lines of code. So it's much more powerful than having to write a reader on your own that reads in the output file. We'll also, for the Green's functions example, perform a simple linear inversion using NumPy, and we'll plot the results using matplotlib. Although I don't believe I have matplotlib on my machine. I do have it on my Linux machine, so we'll maybe see if we may or may not be able to get that to work. Charles did demonstrate it yesterday, but it's basically just being able to show a comparison of the results. So let's march on forward with Green's functions. First, want to sort of give an overview of Green's functions, and there's some differences between computing Green's functions using a finite element approach and using the Okada approach. So in general, we're going to be computing, in any time we're computing Green's functions, we're computing the deformation due to a unit slip at some point on a fault. Now, specifically in our finite element case, we're going to specify 1 meter of slip at a fault vertex, this corresponds to having a value or a coefficient of 1 for that basis function. And so we have a linear variation in our slip field. So that means the slip is going to decrease away from this vertex to 0 at the surrounding vertices. So it is similar but not equivalent to having a uniform slip over some finite area patch, as in an Okada dislocation approach. So what this means is when we do perform an inversion, we're not inverting for uniform patches of slip, but we're inverting for basically the coefficients that specify our linear variation in displacement. So we will have a piecewise linear variation in the slip field on our fault. It will not be made up of uniform or patches of uniform slip as what we would have if we were using computing our Green's functions with Okada. And so that's an important distinction of if you're trying to compare results from an inversion using PyLith compared to an inversion using Okada. And the advantage of using the finite element approach, as I mentioned before, is we can compute Green's functions with arbitrarily complex elastic structure. So the examples we'll cover in this session, the 2D examples will be our examples 2D Green's functions. We'll look specifically at a reverse slip case that's in the reverse directory. And there's 3 steps to this example. We're first going to compute synthetic which are essentially fake observations for an earthquake. Normally, you would be downloading your observations from seismic data or geodetic data. Then we'll compute the displacement at our GPS sites for our Green's functions, and then invert for the fault slip. And this example is covered in section 7.15 of the Pilot User Manual. We'll then look at a 3D case, but in a 3D case, instead of, we'll skip steps 1 and 3, and we'll just be looking at the step 2 of computing the displacement at sites for Green's functions. We won't be doing an inversion, and the utility of this is that it shows the difference between doing a 2D Green's function case and a 3D Green's function case. And in the 3D, we're going to make use of this is step 21 in the example's 3D hex 8 directory. So we've already generated the mesh for that one, and so we'll just be looking at computing the Green's functions. In the 2D case, we'll go through the mesh generation process as well. So for our 2D Green's function example, again, we're in the example's 2D Green's functions reverse. We're going to generate the mesh using Qubit. We'll compute synthetic observations using the earthquake simulation.cfg file. Then we'll compute our displacements using at the GPS sites as well as the ground surface for the Green's functions. This is how we run that problem. We'll invert for the fault slip and then visualize. We'll try to visualize the results using matplotlib. A few words about the Python packages. NumPy and H5Py, they're included within the binary distribution. As we've mentioned before, NumPy or NumPy is similar to numerical functions in MATLAB. It has linear algebra operations. You can create matrices. You can create arrays, 2D, 3D, 4D arrays. And H5Py is the Python wrappers for the HDF5 library. It provides this very high-level access to HDF5 files. Matplotlib is a little more difficult to install if you don't have the binary. So that's why we did not include this in the binary distribution. It's designed to be very similar to MATLAB, and it is available. It's open source from matplotlib.org. So MATLAB has a commercial license, although academic institutions often do have a site license. But if you're looking for a free alternative to MATLAB, when you can combine NumPy along with matplotlib, essentially you have almost all of the functionality of MATLAB for free. Now let's look at our simple linear inversion. And so we're going to form an augmented system of equations where we have our Green's functions, our observations, and this lambda is our penalty parameter, and D is sort of how that penalty parameter is enforced across our observations, and we're going to use sort of the minimum magnitude approach, so D will be diagonal in our case. In the README, you'll see there's a suggestion of using a block diagonal D based on Laplacian that gives you a sort of a smoother enforcement. So it's optimization based on smoothing rather than optimization based on, for our case, minimum moment magnitude with a diagonal matrix. So if we put in a lot of smoothing, it basically will try and minimize the amount of slip. And then as we relax our penalty parameter, we tend to be closer, and we'll see that things sort of tend to saturate, or in terms of the fit. We're using a generalized inverse approach. This is essentially equivalent to a least squares approach. This is the nomenclature that Charles chose to use, that minus G superscript is simply reflecting that this is a generalized inverse and not the true inverse. And so our model estimates are our generalized inverse times our observations. So let's go in. Are there any questions at this point? before we start running these test problems.